We can't assume that the rates of change in the x and y directions are going to be uniform or even nearly uniform over a region this big. However, given a well-behaved function, if we shrink our region of interest down to, let's say, a circle of radius h, where h is small enough that changes in fx and xy are not significant, then we can get a good picture of what happens in the near neighborhood of x naught, y naught. And we're going to be able to get an instantaneous rate at which the value of the function changes with motion in the direction of our u vector. Here we have something that's supposed to represent the small circle around x naught, y naught. Clearly this is not a well-drawn circle. It's much closer to x naught, y naught here than it is here, but we're going to understand this to represent a circle. We can make the radius h of this circle as small as we wish, so that we can limit the, let's say, the percent by which our fx and our fy can change over this region. If the function is well behaved, we can make fx and fy as nearly constant as we wish by making the region small enough. So we simply choose an h small enough that the changes in fx and fy can be considered to be negligible or insignificant. Our unit vector u still has the same direction as before, and if h is very small, u can go on for what would be on this scale a huge distance, miles, light years, whatever. We can make h small enough that the u on this scale could be as large as we wish. Now, this vector that goes from x naught, y naught out to the circle has magnitude h in the same direction as u. U being a unit vector, that means that this vector here will be h times u. We're maintaining the same direction as before, but shrinking the vector down to magnitude h. If ux and uy are the x and y components of our original u vector, then hu is going to have x component hu sub x and y component hu sub y. Assuming that the rate of change of f of x, y in the x direction is f sub x, the x derivative of f, evaluated at the point x naught, y naught, and I'm not going to write in all that notation. We'll make that more rigorous at some point soon. The idea is simply that the change in the value of f due to this displacement hu sub x is going to be delta f approximately equal to fx, which is the rate at which f changes with motion in the x direction, multiplied by how far we go in the x direction, which is our hux. So that delta f is fx times hu sub x. Now this is delta f due to our x displacement. I'm using delta f for the change in the value of f due to the y displacement, using the same symbol because, as I've said, I can't think of a really good way to distinguish those two with notation that at this stage at least wouldn't be misleading. So we're going to say this is the delta f due to the displacement in the x direction, and the delta f due to the displacement in the y direction will very similarly be the product of the displacement hu sub y times the rate of change of y with respect of f with respect to y, in the rate of change of f as we move in the y direction, and we get this expression: delta f equals fy times hu sub y.